Welcome to the new class. Last class we discussed about the definition of a subspace and the prove a subspace theorem for how to verify the any subset of a vector space is a subspace. In this class today we discuss some examples of a subspaces. So let's begin this first. We have to take a W be a polynomial of Px belongs to P2, and the elements of a P2 you know that is the form of a or the form of a A0, A1x, A2x square, and then its condition is imposing this P0 and is equal to P2, and then this is a form a subspace with respect to the usual additions and scalar multiplication of a polynomials. We know that the polynomials simply addition of a polynomials. If we have take a this is equal to p of x, and then we have to take a q of x is equal to a naught. We take some b naught, b1x, p2x square. Then we define a px plus qx in the form of a, this is the form a naught, b naught, a1 b1 x plus a2 plus b2 x square. Similarly, we can say that if we have a alpha times of a px, this is defined as scalar multiplication in the form of a alpha a naught, alpha a1 x, alpha a2 x square. So addition and multiplication is defined into this form. Now we try to show that this W is from a subspace under these two binary operations. So we have to show that first thing is that this 0 should be the 0 polynomials. We have a is the element of a W, and if we take a U and we take any two polynomials P and Q are the elements of a W, then we have to show that this is PQ is also the element of a W, and we have to show that alpha is any element of a real because field is a real, and P is the element of a W. Then we have to show that alpha P is also the element of a W. So these three conditions if we satisfy this, so we can say that this set form a vector space. Now you know that 0 polynomials is nothing but is equal to all the coefficient of a 0 polynomial because P2. So 0 of x is nothing but is equal to you have a 0 plus 0x plus 0x square types, and now we have a 0 of 0 is equal to you have a 0, and 0 of 2 is also is equal to 0. So we can show that 0 of 0 is the same as a 0 of 2. Then clearly 0 polynomials that belongs to the set of this W, then the W is clearly is a non-empty. Now we prove the second under this addition is a closed. So under addition of a sum of polynomials under addition is a core is closed. So that means we can take any two polynomials. If we have to take a P and Q are the two polynomials belongs to the W, and then because it satisfies this condition, so this is P0 is equal to you have a P2 and you have a Q0 is equal to you have a Q2. So in this case we can just say we try to show that if we take a sum of these two polynomials Px and Qx is again we have to satisfy into this form. So now if we have a P plus Q, so it belongs to the W, means we can take a P plus Q over 0, and this is nothing but is equal to, this can be written in the form of a P of 0 plus Q of 0, and then this is P of 0 is equal to P2. This can be written as a P2, this is Q2, and this is nothing but is equal to, we can write P plus Q, again the property of distributive properties, is equal to 2. That means P plus Q0 is the same as a P plus Q 2, and P and Q are the element of this. This implies that we can say that P plus Q is the element of a W. So in this case we can say that trivially this is closed under the under addition. Now we have to take any field of a real number because it's this R, and then we have to take any element of this. We take a alpha times of a p of 0. So we have to, this is alpha times, we have to p of 0, and this is nothing but is equal to alpha times of a p of 2, and this is nothing but equal to alpha p over 2. So in this case also we can say that alpha and p0 is equal to alpha p2. So this means we can say that simply this alpha p is also the element of a W. So this means clearly W satisfy all the three conditions. Under is a non-empty, and also is the under addition is a closed, under scalar multiplication is closed. So this means this W is from a vector subspace, and this is clearly W is a subspace of this thing. Okay, so now we have to move for another example. We take a polynomials, the set of a polynomial of degree less than equal to n with the real coefficients, and the subset I take into this form f, and this integration 0 to 1 fx dx. So this means we have to take a, 0 is also belongs to the Pn. Now 0 we can take a if we take a 0 is W only, in this case we take a 0 to 1 0x dx, and this is clearly is equal to 0. So this means we can say that this means it satisfy this. So this means this implies that this function is belongs to the W. So this is W is clearly is a non-empty. Now if we take any two elements of this W, f and g are the element of a W. If f and g are the element of a W, then f must satisfy this condition. So we have say that f integration 0 to 1 fx dx is equal to 0, and g is also the member of a W, and g is also satisfy this condition. So we can say that integration 0 to 1 gx dx is equal to 0. So we have to show that f plus g, so we have to take a f plus g, and we can take a integration of this, and we say the sum of this integration is again 0. So we can take a 0 to 1 if f plus g is also. So we try to show that f plus g belongs to the W. So we show that f plus g belongs to the f plus g over x dx should be is equal to 0. What we say, because this is a f and g are the functions, and this is a integration by the property of integration, this can be written in the form of a 0 1 fx dx plus 0 1 gx dx. And now because fx dx, because f belongs to the W, this implies that integration 0 to 1 fx dx is equal to 0. This is 0, and this is again gx is 0. So this is sum is equal to 0. This implies that we can say that f plus g is the member of a W. So this means clearly this first condition is a non-empty condition is satisfied, and also the sum of is closed under this addition. So this means clearly this is a satisfy all this property. So this is a belongs to the W. Now we have to. Okay, so now we take any alpha belongs to the field of real, and f is the element of a W. Then we have to show that alpha f belongs to the W. So we take integration over 0 to 1 alpha f over x dx. Alpha is some constant, so we by the property of a integration, this can be written alpha times 0 to 1 fx dx, and because f belongs to W means integration 0 to 1 fx dx should be equal to 0. So this is equal to means this can be written as alpha into 0, and alpha 0 is equal to you have a 0. So this implies that we can say that integration 0 to 1 alpha f x dx is equal to 0. This implies that this alpha f is the element of a W. So in this case also satisfy all the three conditions of the this vector space. So if satisfy all the conditions of this subspace, so then we can say that this is an indication W is a form a subspace of this vector space. Also this is means we have to use the our theorem. We conclude that W is a subspace of a vector space V. Okay, so this should be 0 1. Okay. So now we have to move to the next. Does this set W is belong to the C2? X has a, this is a condition we impose as a imaginary component, so form a subspace of a C2. Clearly answer is a no. Why is no? Because if you take a C2, you can take a I into I comma I is equal to, you have a minus 1 comma minus 1, and minus 1 1 comma minus 1 is does not belong to C, and this is not a purely imaginary condition. So X should be the purely imaginary is there. So this means we take a X is equal to some imaginary conditions, and then we take a alpha is equal to the identity I, then we can say that image. So this is also, this is means it's not closed under the scalar multiplication. So V is not a subspace of a C2. Why? Because this I is equal to minus 1, this is not belong to the C2, and this is not belong to the C2 means this is X is C2, X is imaginary. So this means clearly this element is not belongs to a W also. So this means clearly we can say that by this example. So you can say that clearly is not a subspace. Okay, so now we have to discuss some more examples. I take some different type of example. We take consider a vector space V is equal to R2 with the operations. We take a x1, x2, x1, y1, x2, y2 in the form of x1 plus x2 plus 1, y1 plus y2 minus 2, and we have a scalar multiplication x alpha times xy is equal to alpha x plus alpha minus 1, alpha minus 2 alpha plus 2. So these types we have to define the addition and scalar multiplication. And now examine whether the following subsets of the vector space following sets are subspaces of the vector space V. So we can just first we take a if we take a alpha is equal to 0, then we have a 0 of xy. Then what is the 0 of xy is equal to, you have a 0 sorry, we have to write a 0 into x plus 0 minus 1, and then 0 minus 2 into 0 and plus 2, that is equal to, you have a minus 1 comma 2. So in this case we can just say that this is the additive identity in this case is a minus 1 and 2. Why we have minus 1 and 2? We can just check x1 and y1 plus minus 1 2 can be written as a, by the definition, x1 minus 1 and plus 1, and then you have a y1 we have a this is equal to plus 2 minus 2, and this is clearly you have a given to the x1 and y1, because the property of a additive inverse is equal to u plus 0 is equal to u. So we keep in mind in this questions that is a 0 element of this is 0 element in this case is the form of a minus 1 and 2. So in this case we have a 0 element is we have to keep into a minus 1 and 2 is the 0 element of this thing. So this means we just say that into minus 1 and 2 is a 0 element. So now first we have to just set xy laying on the straight line, y is equal to 0, that means w is the form of this x0 such that x is any real number. This is w is this, we have to check is this is a subspace or not. We need to check is the is additive identity is there, 0 element belongs to there or not. But you can see this is clearly minus 1 comma 2 is does not belong to the w, because minus 1 comma 2 is the 0 element. We can say that 0 in this case we have a minus 1 comma 2 additive identity here in this problem. Here this is the problem. By this we have a this is the additive identity is there. So we keep in mind the 0 element is this is not belong to the w. So this means if it not belong to the w, we cannot say about the subspace of this. So this clearly we can say that this set when a straight line y is equal to 0 means x-axis is not a subspace of the given problem is this thing. So now this is clearly is not a subspace. The answer is clearly no. I just say that. Now we take a laying on the line straight line x is equal to minus 1. So w in this case we have the form of you have a x is equal to minus 1 comma y such that Y is the element of a R. This is a subspace subset, and we have to check, verify this is satisfy all the conditions of the subspace theorem, satisfy or not. Here again we just select identity element is minus 1 comma 2, and then clearly here you can say that minus 1 2 is the element of a W. You take a y is equal to 2, minus 1 2 is belongs to W. This means clearly W is a non-empty. At least identity element belongs to the this set. So if identity element is belong to this set, we can say this is satisfying this condition. Now we have to take any two elements and then verify is under addition is a close or not. So we take suppose U and V are the element of a W. If U and V are the element of a W, then U is the form of a minus 1 comma y1 and V is the element of a minus 1 comma y2, where this y1 and y2 are the real number. Now we can take a U plus V. U plus V is equal to minus 1 comma y1 plus minus 1 comma y2. Now we have to using this property, addition we define into two vectors is defined into this form, where x1 y1 x1 plus y1 this, and then we have to addition we have to, I am just writing here, so x1 y1 plus x2 y2 can be written as a x1 plus x2 minus 1 x2 plus y2 minus 2. So this means this clearly you can see this form. So we have a addition into defined in this form. So we just take a two elements. So this U and we have to already show that this is equal to minus 1 comma 2 is belongs to the W, and U and V are the element of a W, means U is the form of a minus 1 comma y1 and V is the form of a minus 1 comma y2. Now we have to take a U plus V minus 1 comma y1 plus minus 1 comma y2, and this can be written as a form of a minus 1 plus minus 1 and we have a minus 1. So this is clearly we can write in this form. So we can just say that we have to just into this form. Sorry, this is not correct. Okay, this one minus 1 plus this minus 1 plus this. So we can just say that this is minus 1. This is so I just take this is plus. Okay, this is a plus 1 and this is minus 1. So we can just say that sorry here. Okay, this one. Okay, this one is just take a x1 y1 plus x2 y2 is equal to x1 plus x2 plus 1 y1 plus y2 y1 plus y2 minus 2. So this can be written as a minus 1 plus minus 1 plus 1 and then y1 plus y2 minus 2, and this can be written as a minus 1 comma this is y1 plus y2 minus 2, and this is clearly in the element of a W because this is a some element of a real number. So sum of these two again is belongs to this set. So we can say that this implies that U plus V is the element of a W. Now we try to show that scalar multiplication is also belongs to this. So alpha times of a some U, alpha times of a U can be written alpha times of a, we can write alpha times of a minus 1 comma y1, and now a scalar multiplication, so we have to define into the form of a this thing. You had scalar multiplication we define to this form, alpha x plus alpha minus 1, and then we have a alpha minus 2 and this thing. So we have to define in this form. So we have a alpha times of a x1 x2 is equal to alpha x1 plus alpha, I just check minus 1, and then we have a minus 1, then we have a alpha alpha minus 2 alpha, then we have a alpha minus 2 alpha, and plus 1 plus 2, that is equal to this. Scalar multiplication to this is fine. So alpha is equal to alpha multiplication is fine to this form. This can be written as a minus alpha, and then you have a plus alpha, and you have a minus 1, and comma alpha is equal to, you have alpha, and then you have a minus 2 alpha, and then you have a plus 2, and then this is equal to, can be written as a minus 1 comma alpha minus 2 alpha minus 2, and this is nothing but is equal to, again, is the element of a R. So this is whole is the element of a W. So this means we can say that alpha u is also the element of a W. So this means this also closed under the scalar multiplication. Though this means clearly this we can say that this is a straight line, x is equal to minus 1 is a subspace of this. Now we have another, if we have to take a x plus line is equal to this, so we have a W is the form of a, we have to take a elements of this, the form of a, if we take a x and we have a 1 minus x, such that x is the element of a R. So this is a subspace or not. So we just take a, because we take a, if we take a x is equal to 1, so we have a clearly identity element here, you have a minus 1, so you have a minus 1 comma 2 is the element of a W. So this means this is clearly is a W is a non-empty. Now we take a two elements, say u and v are the element of a W, then we can say that this can be written in the form of a, u is the form of a x1 comma 1 minus, yeah, we can write x comma 1 minus x, and v can be written as a y comma 1 minus y, where x and y are the element of a R. Then we take a u plus v. U plus v is the form of a x comma 1 minus x plus y comma 1 minus y, and then addition is again defined the form of a x plus y, you have a plus 1, and then in the form of a y is equal to, you have a x, x is equal to, you have a 1 minus x plus 1 minus y minus 2. So this is in the form of a, we can just say that this is equal to 1, this is can be written in the form of, this is can be written as x plus y plus 1, then you have a we have to just say that we take a minus outside, then this is the form of a this can be written in the form of a this we can just check. So write in the form of a, this equal to 2 is cancel, you have to just take a x plus y, and then this is nothing but is equal to, this can be written as a, if you have a, this thing is equal to x plus y plus 1, and then y should be the 1 minus x types. So this is nothing but is equal to, we have to 1 minus this can be written in the form of a x plus y plus 1, this is 1 minus x plus y, and then plus 1. So if we have a, we take into this form, we have a minus x, and then you have a minus y is here. So this is clearly minus x plus minus plus 1. So this is cancel out, this is in the form of this is clearly into the x plus y, 1 minus x plus y. So this is again is the element of a W. So if again is the element of a W, means we can say that u plus v is the element of a W, and similarly we can show that the alpha u is also the element of a W by the property of a scalar multiplication. Scalar multiplication is alpha x plus alpha, and then you have a minus 1, you have a alpha, you have a minus 2 alpha and plus 2 into this form. So in this case we satisfy both the conditions, so we can say that this x plus y is equal to 1 is a clearly is a line, straight line is a subspace of a this set. Okay, so now I just take a one more exam question. This for each of the following subset of a R3, determine whether it is a subspace of R3. If so, prove it. If it not, a counter example to show some property of the subspaces is not satisfied. Clearly here you can just say that we have a 0 0 are the element of there, so 0 plus 2 into 0 plus 3 into 0 is equal to 0. So we have clearly say that 0 0 0 is the element of this W. Now if we take a u and v are the element of a W, then we can show that u plus v. So u is the element of a W, means u is the element of a W, means u is the element of, suppose, x1, we have a x2, x3, and then this, if u is the element of a W, this is the element of a W, means you have a x1 plus 2x2 plus 3x3 is equal to 0. And again we have a v is the element of a, suppose, y1, y2, y3 is the element of a W, then we have a y1 plus 2y2 plus 3y3 is equal to 0. So if we take a u plus v in addition of this, we can just write in the form of this x1 plus y1, and you have a clearly x2 plus y2, and you have a x3 plus y3, and this can be written in the form of we have to just verify that this is satisfy this condition. So we can write this x1 plus y1 plus 2 times of a x2 plus y2 plus 3 times of a x3 plus y3. This can be written as x1 plus 2x2 plus 3x3, use the associativity and commutativity, and then we can say that y1 plus 2y1 plus 3y3, and this is equal to 0, and this is equal to 0. This means this whole thing is equal to 0. So this is whole thing is equal to 0. This means this is clearly sum is belongs to the W. So this means we can say that u plus v is the element of a W, means it is closed under the addition. Now we take a alpha into u is equal to, you have a alpha times x1, alpha times x2, alpha times x3. So we can say that alpha x1 plus 2 alpha x2 plus 3 alpha x3, and this can be written as a, because alpha is a real number, x1 x2 are the real number, we use the distributive property. This can be written in the form of x1 plus 2x2 plus 3x3, and this is nothing but is equal to alpha into 0 is equal to 0, because this u is in the element of W. So this sum is equal to 0. So this means this is whole belongs to the W, and it means this is satisfy all the three conditions of the 0 0 belong to there, u plus v is also belongs to there, and alpha u is also belongs to there. So clearly we can say that the set is under closed under addition and under scalar multiplication. This form a clearly this form a subgroup of this subspace of this thing. So answer is yes. Now this is clearly is no. Why is no? Because 0 0 is not belongs to there. So 0 plus 2 into 0 plus 3 into 0 is equal to 0 is not equal to 4. So clearly 0 0 0 element is not there. So 0 0 0 is not belongs to the W. So this means W is not a subspace of a given vector space. So this is clearly no. Now we have to just take x1, x2, x3 is equal to 0. So no problem for 0 0 0 is the element of a W. But for this is we take a scale under addition. So for example, I take a u is the element of a 0 1 0, then this is clearly satisfy, you have a 0 into 1 into 0 is equal to 0, satisfy this is clearly the element of a W. And now take a v is equal to 1 0 1, and then you have a 1 into 0 into 1 is equal to 0. This is also the element of a W. Means I take a two different element which is the element of a W. Now if we take a u plus v is equal to, you have a this is 0 1 0 plus 1 0 1, this is nothing but is equal to 1 1 1, and this is basically 1 into 1 into 1 is clearly not equal to 0. So this means this clearly does not belong to the W. So this means this set is not closed under the addition. So if not closed under the addition, then we can say that W2 is not a subspace of a, this can be taken W2, no problem. Okay, so we can, is not a element of a this W2. So this means we can say that W2 is not a subspace of the given vector space of a R3. Okay, so now if we have a this is again true, this is trivial, this is answer is a yes. So why? Because 0 can be written as a 0 can be written into 5 into 0. So we have x1 is equal to 5x3. So 0 0 is belongs to the there. So we can just say that is answer is a yes. Why is answer is a yes? Because 0 0 is there. Now we take a u and v are the element of this w3, and then u is the element of this x1, x2, x3. V is the element of this y1, y2, y3. Then you have x1 is equal to 5 of x3, and this is equal to y1 is the same as a 5 of y3. Now we take a u plus v. U plus v can be written in the form of a x1, x2, x3 plus y1, y2, y3. This is nothing but is equal to x1 plus y1, x2 plus y2, x2 plus y2, x3 plus y3. Now we have to verify that x1 plus y1 is equal to this. So we just take a x1 plus y1 is the same as a 5 of this. So we take a x1 plus y1. This is equal to written as the form of a 5 of x3 plus 5 of y3, and this is 5 can be distributive property x3 plus y3. So we have to say that x1 plus y1 is equal to 5 times of this. So this is the element of a w, means u plus v is closed under the under addition. So this means this is satisfy this condition. Now alpha u, if alpha u is the element of a alpha times of x1, alpha times of x2, alpha times of x3. Now we have to show that alpha times of x1 can be written as alpha times of a 5x3. This is nothing but equal to, we can take a 5 alpha times of x3. So alpha x1 is equal to 5 times of alpha x3. So this is the element of a this means this satisfy this condition. So means we can say that this is the element of a w. So w satisfy all the properties of a vector space. Under addition is a closed, under scalar multiplication is a closed. So we can say that this w3 is from a subspace of a vector space of a this R3. Okay, so now just conclude this session by this question. We take any element for w p3, px is the element of this form, and condition is this: you have a minus 2b is equal to 0. So this means you can take a minus 2b is equal to 0. So 8 we take 8x cube plus 4, and that is clearly this is belong to the w. Why? Because if we take a 8 minus 8 is equal to 0, so this is clearly satisfy this condition. But if we take a some element is equal to 4x square plus 2, this is clearly not satisfied into the w, because this we have to need into a this types of a term is there, only x cube is there. So this is the term is a x square is there. So now we check is this form a subspace or not. It's clearly 0 0 is there. 0 polynomials can be written in the form of a 0x cube plus 0, and this is satisfied. This is equal to 0 minus 2 into 0 is equal to 0. So 0 is the element of a this is w. Now we take a polynomials p and q. We have to take a p of x is the element of a ax cube plus b with the condition of a minus 2b is equal to 0. Now we take a qx is the element of a some a1 x cube plus some b1, where is a a1 minus 2b1 is equal to 0. Now we take a p plus q over x is the same as we can write as a px plus qx, and px is equal to, you have a x cube plus b, and plus you have a a1 x cube plus b1. This can be written as a plus a1 x cube plus b plus b1. Now we can show that if this condition is hold, so we can just verify this. We have a a1 plus a2 minus 2 times of a b plus b1. This can be written as a A1 plus A2 minus 2B minus 2B1. This can be written in the form of A minus 2B plus A2 minus 2 times, sorry, A1, sorry, this is A and this is A1. So this is okay, this is A1 minus 2B1, and then this is equal to 0, this is 0, so this 0 plus 0 is equal to 0. So this means we can say that this P plus Q is the element of this W. Now it's closed. Now we have to check alpha times of a Px. This means we can say that alpha A x cube plus alpha B. Now we have to check is this satisfy this. So alpha A minus 2 times of alpha B. This can be written as alpha distributive property alpha minus 2B, and this is alpha into 0 is equal to 0. So this implies that alpha of P is also the element of a W. That means W satisfy all the properties of this vector space. So this means this satisfy all the 3 properties of subspaces. So this means clearly we can say that this is a subspace of a given vector space. So now I just stop today's lecture here, and in the next class we discuss some properties of this different types of vector spaces, subspaces. We have to take a intersection and sum of a subspaces, and how to discuss into this one. Thank you very much.